Drop an iron nail into water, and it falls straight to the bottom, but drop a massive log in, and it bobs on the surface. If weight were the only factor at play, that log would be sitting on the floor of the tank. Weight alone doesn't determine what stays on top and what goes under. The actual rule of the water is density. It's the relationship between the weight of an object, its mass, and the physical space it occupies, its volume. Think of two identical backpacks. They take up the same amount of space, but if you fill one with lead weights and the other with feathers, lifting them tells two very different stories. Density measures how tightly packed that stuff is inside that space. It's the difference between a loose pile and a compressed block. Understanding how matter is packed inside an object is the only way to predict exactly how it will interact with the environment around it. We calculate density by dividing an object's mass by its volume. Finding mass is straightforward. Just place it on a scale. But for an irregularly shaped rock, drop it into a water cylinder. The rising water level reveals the rock's exact volume through displacement. By quantifying both the invisible mass and that awkward volume, we can calculate the exact density of any object in the universe. Water serves as the universal baseline for this comparison. In our physics, 1 milliliter of water weighs exactly 1 gram. We use this 1-to-1 ratio to find the relative density of other objects. We compare their packing against water's perfect 1 gram per milliliter baseline to see which one is heavier for its size. This creates a physical struggle called Archimedes' principle. As an object pushes into the water, that water pushes back with an upward force equal to the weight of the liquid the object displaced. Even though a modern cruise ship is built from 80,000 tons of steel, a material far denser than water, it glides effortlessly across the ocean. The hull wraps around a massive interior of air. Because air is light, the ship's average density remains lower than the water. This same logic applies to icebergs. Freezing water forms a crystalline lattice holding more empty space than liquid water, allowing it to float. Buoyancy isn't determined by the heavy materials we use, but by how we arrange materials and their empty spaces relative to the water around them. We can also manipulate buoyancy by changing the water itself. Drop a raw egg into a glass of tap water, and it immediately sinks to the bottom. Dissolving salt into the water adds mass to the liquid without significantly changing how much space it takes up. The liquid essentially becomes more crowded with matter. As the water's density surpasses that of the egg, the physics of the environment shift, and the heavy egg is forced to float. This occurs naturally in the Dead Sea. Because the salt concentration is so high, the water is dense enough to hold a human being high on the surface without any effort. By altering the chemical makeup of an environment, nature and humans can actively reverse the rules of sinking and floating. Dissolving salt into water also alters its freezing point. On winter roads, that salt prevents ice crystals from forming even when the temperature drops below zero, keeping the pavement clear. Liquids can also hold dissolved gases, like oxygen. In cold mountain streams, that invisible oxygen provides the lifeline required for aquatic life to survive. Rising temperatures force these dissolved gases to escape. A warm soda can't hold on to its carbon dioxide, causing the gas to rush out of the liquid as soon as the pressure is released. We even use these principles to save human lives through oral rehydration solutions. An ORS is a uniform mixture of salt, sugar, and water used to treat medical emergencies. Because the solution is perfectly uniform, every sip contains the exact same ratio of electrolytes needed to rehydrate cells. From engineering massive ships to stabilizing heart rates with a simple drink, mastering the relationship between matter, space, and solutions allows us to protect life in the physical world.